All right, let's go ahead and get started. Armin, do you want to go ahead and share the presentation since you'll be doing most of it?
Yeah, sure. No, we don't want to start from here. We want to start from here. That'll be easy if we start from there, right?
All right. Thank you, everyone, for joining us. This is meeting 16 of the technical working group of OpenEEmeter. And if you can go to the next slide. So today's agenda, we'll be going over a recap of the last meeting and some events of importance, as well as talking a bit about how we are changing our model from R&D to the OpenEEmeter standard, the progress of the hyperparameters optimization, and as well as future work. Next slide. So to start off with, for those of you unfamiliar, we did a presentation talking about the release of OpenEEmeter 4.0 and the daily model specifically. If you're interested, you can watch that video. To find it, all you need to do is Google Linux Foundation Energy and OpenEEmeter, and it will pop up with a link to the video as well as the presentation slides and all of that. Last week we talked about, or not last week, the last meeting, we talked about the LSTM model, and we basically summed it all up in that it's very expensive to run as far as time. It's not much better in test error, and overall we think that given the amount of data that we are putting into it, the reason for all of this is basically that an LSTM is overkill for the amount of data that we're adding to it. Additionally, we found that as far as speed goes, our new model is 11 times faster than the original Caltrack 2.0 model, hourly model. And so we're very excited on that front as well. And then we also introduced the idea that in our new model, we are allowing new inputs such as GHI, as well as arbitrary supplemental data. And then next slide, please. And now I will be passing it off to Armin to talk about the most recent work that we've been performing on the hourly model.
Hi, everyone. So, one of the main things that I've been doing the past couple of weeks after the last meeting, I was trying to transfer all of the code base from the R&D phase to the OpenEEmeter API platform. And we had two main goals for it. One is to finalize the hourly model. And within doing that, we wanted to transfer the code to the OpenEEM API in a way that we want it to be compatible with all of those structure that Travis and the other team members made for the hourly and daily model with different versioning that we update the versioning in the couple of last months. And in doing that, we wanted to check the implementation consistency whenever you transferring the code in different files, in different setups. You always want to check the results that, for example, the test result for some specific random subsample that you had in the R&D code base is actually matching the one that you're getting from the new code base in the OpenEEmeter. So that was one of the main goals of this code base transfer. And the other one was to actually optimize the hyperparameters of the model based on the data set that I'll explain in the next slide. And with doing that, we wanted to avoid any discrepancy between the R&D code and OpenEEmeter in a way that we could optimize the model in the R&D phase, but we should have done that with the same thing with the with the API that we wanted to develop, and that was just like too much work. And then we transferred them and then optimized on top of the new API. And during all of those this process of optimizing the hyperparameters, I could be able to actually debug the code, which is always a good thing. You never know, small bugs can pop up everywhere, and that was a good practice. It wasn't a test for the whole API, but that was a good initial test for it. And based on the work that Travis and other team members done for the daily model, updating the OEEM API previously for the hourly model, for the daily model, it was a really simple and seamless transferring process because everything was in the place. I just need to actually plug it in and plug my new model. And it was really simple. It took me almost 2 days to do the whole transfer and all of the debugging that I wanted to do. So that was a promising thing, that it was way quicker than the daily model implementation that Travis should have done all of the reform, the whole structure of the OpenEEmeter API. So that was easy. And about the model details that we have, we wanted to have the same fit and predict structure that we already have with the current hourly model in terms of simplicity. So initiate the model, model.fit, trains the model, model.predict, give it give the model the input, and it will predict that period of time, counterfactual. And inside of the model, we get the input, but inside of the model, we do the feature extraction, which is suitable to the elastic net, the main elastic model that we have. And based on that feature, we do the fit and predict. So this is a schema of what do we have in the OpenEEmeter right now. Within the model folders, we have billing, daily, and the current Caltrack hourly is under hourly Caltrack. But in my branch, I'm working on the new hourly model. Basically, as simple as that, we initiate some parameters and settings, and we have two main methods, which is fit and predict. But inside of each of them, we have helper functions, which calls the prepare features, which means we get the input data, which it will be a class data, which I'll talk about it in the last slide. We prepare the features for the current set of the model that we have and use it in the fit and predict model. It's not finalized, but that's the whole structure, and that's the one that we are using for the hyperparameter optimization. So let's move on to the hyperparameter optimization. And what do we mean by that? So ElasticNet has two main parts. One of them is the simple linear regression, which the loss function for it is mean square error. And there is a normalization section or part to it that actually tries to limit the coefficients in a way that we have a well-fit model, not overfit model. So if we remove this normalization, we're going to have a linear regression, and we can optimize on top of the train set, which in our case can be defined as baseline. And we're doing great in the baseline as the current Caltrack hourly is doing, but we're not doing a good job for the reporting year or the test set. In order to do that, as we explained in the previous presentations, we're using normalization factors, which is consists of two main elements, L1 and L2 norm. And L1 norm is basically responsible generally is responsible for making the model as sparse as possible. So push those parameters and coefficients to zero, and basically feature selection. And L2 norm is actually responsible for restricting and minimizing the size of those coefficients. So this is the main difference of L1 and L2. And to do that, we have two knobs to turn and adjust to basically find the best solution or the well-fit model. So at the end, the loss function is MSE, mean square error, plus alpha, which is one of those knobs, multiply by that normalization section. And inside of that normalization, we have L1 portion and L2 portion. And this is changing based on L1 ratio or lambda here. So if lambda is 0, we are focusing on L2. If it's 1, we're just focusing on L1. And it can be somewhere in between 0 and 1. So let's talk about optimization setups. What are the variables that we wanted to optimize? L1 ratio, gamma, and alpha, which is that the main portion, the multiplier for the regularizations. So the data set that we're using, we have 12 subsamples. When I say subsamples, means a small portion of data. We couldn't just load all of the data, all of the data in terms of hourly, the features and everything inside of memory. It was better to segment the data, and that's why we call them subsample. Inside of each subsample, we have 250 IDs, 250 meters. And for those, you remember pretty much 5, 6 presentations before, we're using k-folds, 12 k-folds. We have 3 years worth of data, and we are shifting 1 month at a time, and we have 12 k-folds. So basically, we are training 12 different models for each meter. We can kind of assume that we have 250 multiplied by 12 IDs, or 3,000 different models inside of each subsamples. 6 of these subsamples are solar meters, and 6 of these subsamples are non-solar meters. In total, we have 36,000 models, and half of it is for non-solar and half of it for solar meters. The algorithm that we're using is a global optimization algorithm, is RBF opt. I'm not going to go in detail. If you have any question, I will reference Travis to that. He's an expert on that. And for the objective function, we want to look at the average test PNRMSE. So a recap, PNRMSE is person normalized root mean square error. That was the error that we defined. We define an opposite, not the opposite, but instead of CVRMC. And for the test side, we are talking about we're training on train set and we're testing on test set. And that's the most important part for us. And we average all of those PNRMSs on the test set. We have one value for each meter, for each subsample, or for each population we consider. That's the one we wanted to minimize in this optimization problem. So in order to do that and look at different sides of this optimization, or how we are doing, and for further analysis, which I'll explain in the next couple of slides, one time we ran the whole optimization for the whole data set. So 36,000 models. Each model is training on any year, testing on the next year or the test year that we define. And we look at all the data at the same time, optimize the variables. So we call them global optima, the result of that optimization. And for our own research purpose analysis, we try to optimize within each subsample as well. So we have 12 subsamples. We just once at a time grab one of those subsamples and optimize the model, the alpha and L1 ratio. So we have 12 different pair of hyperparameters, optimal values for them as well. I'll explain that why we did that later. Not that much later, pretty much here. So what are we looking at here? We are looking at those optimal values for the optimization runs that we had. So remember, 12 for subsamples. So we have 12 pairs, as you can see. We have 6 blue dots, which is represent the non-solar meter subsamples. And we have 6 red triangle, which shows the solar meter subsamples optimal value. And we're talking about x-axis as alpha, y-axis as L1 ratio or lambda. And the star, the black star, is actually the global optima, which we look at all of the data. That's the optimal value for it. One thing in the global optima, the alpha is 0.22 and lambda is 0.05. If you remember, previously we had like a grid search before, and the optimal value for that was 0.1 and 0.1. Because that the grid that we were searching on it was manual, and it was based on 0.1 to 0.2 and all of those things. Now we have the global optima, which is these are the optimal value numbers for it. And as you can see here, we have anomaly subsample. This is actually that was totally random. I didn't expect this, but fortunately we have that. I said fortunately because I'll explain it in a couple of slides that this is actually a good thing for us to look at it. It was random, but that was a good point of view of why we why we have this anomaly, and what's the impact of this in the global optimization.
Hey, Armin, can we pause here and
Yeah.
just see if folks have any questions? You've
Sure.
covered a lot of ground.
Yeah.
And no dumb questions, folks. I have plenty of dumb questions myself. What questions do people have? Glenn.
Sorry, I joined a couple of minutes late, so sorry if I missed it. Is this for both the hourly and the daily, or this is for the daily only?
Just for the hourly model.
Okay, got it.
Yeah.
Thank you.
Yeah, Glenn, I'm not sure we might have not been graced by your presence the last couple of meetings, but the hourly model we're now fully onto the hourly model, and the daily model is fully released. So the daily model is out in the wild. It is officially, like the OpenEEmeter 4.0 is released, and that is available for use, and that is 100% final at this point.
Cool. Thanks for the update. Yeah, sorry I haven't been able to join recently.
No, it's all good. It's all good. I'm actually glad you're here today. Just if for no other reason to be able to tell you that.
Cool. Thanks, Adam.
And Glenn, if you're interested, Adam and I did a presentation with the Linux Foundation Energy on OpenEEmeter 4.0. If you want to watch the video for that, you can just search Linux Foundation Energy OpenEEmeter, and it'll pop right up for you.
Awesome. Thank you. Looking forward to seeing it.
So can I just a question about this particular visualization here? The two axes are the values for those two hyperparameters. And so obviously for each one of the runs, you had sort of some kind of combined metric for what the PNRMSE was for each of the populations with particular settings, right? Because then you've identified one as being the global optimum, but there's no, you're not representing on this chart anywhere like for each one of those combinations how the PNRMSE value or other sort of quality metrics compare in each one of those, because each one of those is a subpopulation,
Exactly.
right?
Yeah. In the next slide, I would show that.
Oh,
yeah.
I'll stay tuned.
Okay, if there's no further question, I'll go to the next slide, which is a sub analysis, I can say, for not all of these points, but some of them. There's a combination of. Okay, let me go to the next slide. So I need to define what I've done here. So this is a little bit hard to explain. Let's say we have 3 scenarios. One is the global optimal scenario, which we plug in the alpha and L1 ratio, the values for the global optimal that we had here, which is 0.22 and 0.05. Okay, and we train the models for the whole subsamples. Inside of each subsample, we plug this in and train the models for almost 3,000 IDs or 3,000 models, and calculate the test PNRMSE for each meter, average all of that through the population or the subsample, and we have one number. So that would be our average test error for that specific subsample with the global optima. We do the same thing with the subsample optima that we had, all of these numbers. So plug it in for each subsample and calculate the average test PNR-MSE. And the percent difference of that for this subsample and global optima for each subsample is being shown on the blue triangles. That's one of them. We do the same thing when the alpha is 0. So basically, we are removing the whole normalization. All we have the MSE. And plug it in, 0, each subsample, one test RMSE, average test RMSE for each subsample, and look at the percent difference of that overfit model, which I'll explain why I call it overfit, compared to the global optimal value. So one thing, why we call it overfit when alpha is 0? Because we don't have any normalization, anything that can restrict the coefficients. So we are basically overtraining on the training set, not overtraining, overfitting on the training set. We're doing a good job in the training set, but not a good job in the test set. That was the very beginning argument that we had about current Caltech hourly. That's why we added that normalization, and we have the elasticity. So as we can see, for the overfit model, we have almost 8% worse test error compared to the global optimum. Okay, so for each subsample, so we had 12 subsamples for each of them. Some of them even worse, 10%. Some of them is 5%. But on average, we have 8% worse train error. For the subsample optima, we can see that this difference is almost 0 throughout all of the subsamples. So two main takeaway here. One, optimization is working, and actually we need that optimization for the alpha and L1 ratio, because otherwise we can get overfit. We can do worse. We can do underfit, or we can do overfit actually. And global optima is robust for all samples. What do I mean by that? Even though we had an anomaly here, that's why we have that global optima kind of skewed away from the general area of the optimal value used for each subsample. And have that in mind, each subsample is randomly selected. So these are random samples as subsamples. So optimization is working, and global optima is robust, even though we had that abnormal data. I'm emphasizing abnormal. We didn't intend to do that, but unfortunately we had it. But fortunately for us, that it gives us a unique point of view that this global optima is actually a good thing, actually global, actually meaningful for all of the subsamples. I just stop here because that was lots of stuff that I was talking about. Is there any question?
Just to clarify, all the PNR-MSE here shown is the test PNR-MSE, not the train?
Yes, test error difference.
Can I try to sum, because this is literally the first time I've seen this slide myself. Can I try to summarize what you said back to you? Or I mean,
yeah.
So if you go back to the previous slide, we took a look at these these dozen samples. Half of them are solar meters, half of them are non-solar meters. It's pretty clear that if you were only optimizing this model for solar meters, or you were only optimizing this model for non-solar meters, you would get slightly different hyperparameters that would be optimal. But ideally, we would very much like the model to not have to have different parameters for solar versus non-solar.
Yes.
So we're looking at what happens when you take this sort of average of all of these samples and the error on the test set, and looking at this alpha parameter and the lambda parameter. And that's this black star. So now when we set the hyperparameters alpha and lambda to the values at that black star, 0.22 and 0.05. And if we go to the next slide, well, hold on, stay here for a sec. Then that black star is clearly a little bit different than where the optimum would be for any individual subsample that we're looking at.
Yes.
So now we're going to apply the values at that black star, and we're going to compare them to the optimal values that we would get in any one of those individual subsamples. And we're going to see
Exactly.
how distinct are the error patterns that we're seeing on the test sets.
Yes.
Now let's go to the next slide. And those results are that blue line.
Yes.
So the blue line is super close to 0. So that's telling us that the fact that the optimum value from all of the subsamples, taking the average, is giving us very, very similar results to the optimal values that you would observe within any one of the specific subsamples. That is very, very good news, because it's telling us that the model is not super sensitive to these hyperparameters.
Yes.
But what it really is sensitive to is the elastic net fitting, where we are downweighting the coefficients in the linear regression. Because if we remove that downweighting, then we get a sample that has 8-10% error, additional error in the test set above what we would expect from the training set. And that's why you're calling it overfit. So the fact that we're using an elastic net regression and not just a very simple linear regression is very, very important as well. And it's definitely improving the model's performance by a large amount. Is that a fair summary?
That was perfect.
Okay.
I wish you could, explain it instead of me.
No, man. You did a good job. I think it's just like sometimes it helps when somebody who's like not nearly as smart can explain it to everybody else. So good stuff.
That was a really good summary of all of the things that I've said.
So can I? I think this answered one of the questions that came up as you were talking, Adam. Is I was realizing how much that outlier had pulled the quote unquote global optima, and I had this pang all of a sudden. I was like, oh no, what if it's ruining everything? We should be doing some kind of a parabolic blah blah blah. And then when you explain this, and I caught up with the meaning of the blue line, the answer is, you know what, it doesn't matter that much.
We ran into a similar situation actually in the daily model, where we were doing some hyperparameter tuning. Travis, I'm sure, remembers the details a lot more than I do, but I remember we all breathed kind of a sigh of relief when we saw that those parameters were fairly insensitive. And I think one of the things we're consistently reminded of, and we try to be cognizant of, is we don't have samples from like all over the country. We don't have samples on an enormous array of like distinct usage patterns and stuff like that. We're working with the data that we have, right? And we don't have everybody's data everywhere. So it's very good to see these kinds of results, which give us some indication that, like, look, the fact that we're not seeing these subsamples be super distinct. I think one thing we could do is, we're clearly seeing a difference between like solar and non-solar. How much difference, this analysis would be super interesting if we specifically created differentiation between the samples and didn't take random samples even within these subsamples. Like maybe we look at high users versus low users, or like high cooling versus low cooling, those kinds of things. That could also be something helpful. And just if Armin hasn't said it already, we'll also be looking at commercial here. Like we're at the very least, we're going to also look at commercial and work that into this analysis and make sure that we don't see like massive differences, or or that at the very least commercial is feeding into like what is that optimization.
I have a hunch I know the answer.
sorry, just a quick, this is probably an easy one, but you're pointing out that you don't have the opportunity to run this on data from all over the country. Some of the rest of us might have data from other climates. I'm guessing that the process that you've gone through to do all the steps that you're showing the results of here is sufficiently complicated and done as a one-off that like you don't have a packaged release for it that we could like easily feed in a few thousand meters from somewhere else in the country and then just like spit back the charts at the next meeting and show you if it's any different in other climates. That would probably be a big lift, right?
As of now, I don't think we have something ready that you can plug it in because we are using that 3 years rolling data. So the hard part for the modeling is that feature extraction from the main input data. That's why we're trying to do the data class, which I'll explain in the future work slide. I think it's a little bit soon to do that right now.
So
Yeah,
a couple
I
things.
wasn't expecting it, but I thought I'd ask. Go ahead.
So as far as the concern about that anomalous subsample, despite how good the optimized value is, that's still a concern because we can do better. And if we can do better, we're already in the guts of it. We may as well. So this is future work, but we're talking about ways that we can reduce the effect of anomalous models. Now, the other thing that I was thinking of is as far as the concern about are these variables globally predictable or I can't think of the word, globally valid. I intend to go towards yes, they are, because these variables are not specific to anything going on within the model. It's purely about are we rejecting, basically downweighting a coefficient or not? And that tends to be just, is the general structure of the data somewhat similar? And the electrical use or gas usage of various buildings, while they might be very different as from each other when we're sitting there staring at them, when we're talking about it more from the perspective of like a data science perspective, they're really not that different. So these coefficients tend to be much more globally applicable, as you could see on that next slide when the global value is clearly different, but and yet we're so close to zero. So it's already very, very close.
Andres from SCE asked a good question. I just want to, and Travis answered it, but I want to take a moment here to just explain this because it's kind of a super important point actually. And you know, any model, you have to make a determination based on how it performs, you know, during like a baseline period where you're training on data, and then you're going to use that model to develop a counterfactual. You got to have some understanding of, you know, is this model a good model? Is it a bad model? Should it be trusted? Should it not be trusted? And the metric that we've used for years, and I think the industry has used and kind of has, it's become a standard practice, is the CVRMSE, the coefficient of variation of the root mean squared error. It's basically a normalized root mean squared error. And the fact is that model or that metric can fail wildly when you have average values that you're normalizing on that are close to zero. And when can that happen in the world of energy? Well, it can happen when you have solar PV customers, right? And Travis makes this point quite a bit that, look, you get some solar PV installer out to your house. And, you know, I actually had a guy come out a few weeks ago and was doing a little bit of work on our roof. And I asked him about solar PV. And he said, the city of Fort Collins allows me to size your system only 10% greater than your total annual consumption. So I would need to look at your electricity bills, and then I can go at most 10% more than that. So what is he saying really? He's saying, I can size your solar system to use so that it generates as much electricity as you're using. In other words, you're using a net of zero, which is exactly that situation. So we wind up with CVRMSE values for solar PV customers that just absolutely blow up. And like one of the biggest reasons we're here, like in the first place, doing this new hourly model development is to make sure that the hourly model can perform well for solar PV customers. The existing like Caltrack 2.0 model does not perform very well for solar PV customers because it's not aware of solar irradiance data for one, and we're using metrics like the CVRMSE that don't actually give us a lot of insight in comparison to non-solar customers. So, Andres, I just wanted to take advantage of the fact that you asked that question to kind of remotivate the whole concept of like why we're moving away from CVRMSE. Now the question is like, what is PNRMSE? And this is basically instead of normalizing by the average value, which can be close to zero again for solar PV customers, we're averaging by the interquartile range. And so that's a value that has, it's just the absolute value of the interquartile range. And that actually, we've shown in a previous meeting that gives us a very, very close relationship to CVRMSE. Like the correlation between those metrics is quite high. And Ethan actually was the one who came up with the suggestion to kind of study, should you use the 5th versus 95th percentile, the 90th versus the 10? And interestingly enough, the optimization just landed on the interquartile range. So that's what the PNRMSE is. It's the RMSE divided by the absolute value of the interquartile range, and it's a much more reliable error metric, and it's comparable between solar and non-solar. So hopefully that makes sense to folks.
Okay. So if there's no question, I'm going to move to the next slide. So let me go back again real quick. So most of the time here, the subsamples act normal. Although they're random, but they act kind of similar to like each other. For the non-solar meters and solar meters, they're so close. But one of them was acting weird, and I saw that in the tester before, but I kind of ignored it. I thought probably inside of it there's weird behavior of meters or something. It wasn't as big of a deal for me before because it was performing, even the new model was performing better than Caltrack, the current Caltrack model. So I didn't dig into it. But fortunately for us, that popped up in this optimization. The figure that we were looking at is for a normal sample, one of those subsamples that we had. And we are showing the average trained PNRMSE versus average test PNRMSE. And each dot shows 1 meter ID, which means, for example, here, the average trained PNRMSE for that is almost half, but the test set is almost 3. It's a little bit different. They're a little bit different, but that's basically the average value for the new model. And this is for the subsample optimal value. That can be plotted for any different alpha and lambda that we had, but this is just for the subsample optimal. This is a normal population or subsample looks like. And for that specific abnormal subsample, which is here, which is number 3, and it's non-solar. It's something that I saved in my code. So this is the abnormal sample. This is for that specific subsample. 99% of, more than 99% of the values for those meters, PNRMSE, average cis PNRMSE, are like, it's inside of this concentrated, pretty much a dot. But I'll show this specific region in the next slide. But there are a couple of them, couple of meters that are actually acting differently. I believe this is 1 meter because we are using the 12K fold, and this is just 1 meter has a value of 1e to the power of 30 something. I don't know. I'm not sure. I didn't have the time to dig into it. But my guess is that one of the IDs has a huge abnormal value that it's not 0, it's not infinity. that swing away all of the test PNRC, and unfortunately, it's right in the middle of the 3-year window, so it's somewhere either in the test set or in the train set. So if we remove these values here, just for a second, let's just imagine we didn't have this ID or some or meters. This would be that subsample. This would be that abnormal subsample, excluding those anomalies. Again, looks pretty normal to me, the way it treats this scatter plot. So one of the things that we need to consider in the future work, let me just jump into the future work actually. One of the things that we need to consider is commercial samples that can add extra variable in terms of the pattern and behavior of electricity consumption in a way that actually can swing that optimal value. I don't know how it would impact it, but that's one of the things we have to check. And so far, we were optimizing the models based on temperature and GHI as the time series values for both solar and non-solar customers. We want to be consistent. And now we wanted to change it to the temperature only to see how the whole optimization would change. Does it change the optimal value a lot? If it doesn't, or if it does, how far away we are from when we are using GHI. And that anomaly subsample actually showed us that we need to either restrict the impact of those anomalies, like downweight them based on their magnitude compared to the other meters in the population, or we just remove them with an anomaly detection algorithm and then just remove them as easy as that. And one of the other things that we wanted to do, finalize the model, as I show you in the code base inside of the OpenEEmeter API. And we wanted to have a data class, which would be the input of the model. We wanted to introduce this data class to be consistent through all of the models. So you just pass the model to the data class, and any data preparation, any disqualification or anything can happen inside of that. And the clean data goes to the model, so we have less headache. And that could be true for all of the models that we have. And one of the questions that we had in the previous future work, which we didn't work on it, and we didn't answer it, should supplemental data be restricted? The supplemental data, for those who were in the previous presentation, it's actually an extra data. For example, you have operational time series or EV schedule, like you know that there's a time series of 0 and 1s, and 1s show the time that you're actually charging the EV. You don't know the value, but you know that's charging. That can be a supplemental data, and we show that that actually can be very, very helpful if that data is dependent to that supplemental data. So these are the future work that we have to do. Okay, now questions. Yeah, go ahead, Mustafa.
Thank you for the good work. I have two questions, and I had that kind of conversation over the GitHub with Travis for the daily model. When the facility or the equipment reach out the maximum capacity, so when we have a regression there, at some point we need to split them based on the maximum capacity of the equipment, either the solar kind of PV or heating and cooling kind of devices. I didn't see that one in the daily kind of modeling, and I provided one example there to show how big could be in the extreme kind of weather condition. My kind of question, particularly for this PV, what we have seen for the panels, for the electric panel, over the time, the efficiency of the generation reduce. And for example, when you compare the data for the year 1 and compare it with the year 2 or year 3, the efficiency of that solar panel itself change over the time. Having said that, it can be easily addressed by a weighting factor, like weighting factor over the time. I was wondering if you already consider that weighting factor to decay the kind of that impact of the efficiency, or this is something else that should be considered in future?
Not really. I think that decay weighting is more related to the solar disaggregation, because there's no way that right now we can say that weighting can impact just the solar customer or the solar value of that, because it's a mix of electricity consumption. On top of that, you have solar generation. So it's a summation of that. The best thing that we can do is to use GHI to replicate that that generation. Even though, imagine, even throughout all of the years, like even 5 years, we don't have any reduction in the efficiency, but the load can change. Even if that doesn't change, still with the current modeling, the way that we are modeling, we don't estimate the size or just the generation of PV panels. So there is no such a way that even everything is stay the same, we can say that efficiency can be explained by these coefficients that already we have. So I don't think in this problem setup that already we have, we can introduce that. And I think that's a good idea for next set of problem that we wanted to solve, is which is a solar disaggregation. Travis, if you have anything to add.
No, though I did not hear a second question, and I thought there was two.
That's it. So my other question was related to the maximum capacity of the equipment. So when you look at the like equipment, it's possible that with the data that you have, there isn't any impact from the capacity of the equipment. In a specific condition, those equipment may reach the maximum load, and after that, you don't see any change in the consumption, in the electricity consumption, because they pretty much reach out their maximum energy consumption, or for the PV generation, right? You may consider, for example, when you have all cloudy kind of situations for the baseline modeling, and you consider that one to develop the model, and then after a while, in a specific region zone, you have all sunny kind of condition, so you don't see it in the baseline.
One thing that I can suggest is that first of all, I think for the majority of the meters, we're not going to have the sizing or anything related to the detail about the PV solar panel system, any detail or any info. If we have, that could be for a specific one project that the vendors can provide us with those type of data set. I mean, if we have that type of data set, that actually can be really helpful for me, specifically because I'm working on another project with solar disaggregation, and I'm kind of predicting the size on detail about the solar PV systems. But normally we don't have those type of data. But the alternative to that, for this problem setup that we have, is to actually kind of calculate that saturation or anything that some person that has available data for example, efficiency throughout the time, or the saturation or capacity, or anything that can be defined as a time series or as extra supplemental data. I'm not sure if we can if we want to make that available to everyone, but that's going to be a R&D phase that you can just actually provide the model with that supplemental data and see the impact in the future. That's exactly comes to the last item in the future work. Should supplemental data be restricted, or anyone can use any sort of data set that they want? I would say we need to restrict it so we can have more consistency throughout this open source API for the prediction or counterfactual, but that's something that we can discuss.
Okay, thank you.
So,
It's a good point. I just want to say,
go ahead.
Ethan, sorry, just want really quick, just to before we change topics. I think it's definitely a good point that solar PV systems can hit a saturation point, or other systems can hit a saturation point. But if we're thinking specifically about solar PV, I mean, it definitely can happen, and we've seen that with some previous modeling that we've done, and there's always a give and take on like how specific do you want to get with your model, and how much time and effort do you have to put into it. And I think that right now we're kind of at a point where we want to finalize this model as it exists, doing these things that Armin is talking about here, for instance, making sure we have commercial samples, and then we have an open working group and we can continue down these roads if we'd like to. So if there are, opportunities to look at introducing probing for solar PV saturation and how we would adjust the model to, be trying to track and modify for those things, then, it's definitely on the table. So it's a good point, and duly noted.
So if I can continue on that topic, and not to push harder for more overfit models and more on-site data, I'm on team automation here, and it's not to like have a religious war about physical models versus empirical models, but I think the best way for models like ours to deal with saturated HVAC and saturated inverters is to have a model coefficient that is able to, have another degree of flexibility that looks for, that part of the temperature range or GHI range, and is able to respond differently to it instead of just going linear over the whole space. And so this question is really just about understanding sort of how many degrees of flexibility we have in this new models, just so we understand what the limitations of the model are. So for example, the Pacific Northwest had the heat dome a few years ago, and like basically all the models broke because no models had ever been fit on 115-degree temperature in Oregon. Like we don't know what the HVAC systems do until it happens. So there's always limitations. You don't understand what they are. Can you remind me, like we've gone so deep down into like the hyperparameter discussions and stuff, I actually lost track of whether we are still optimizing coefficients around a binned linear partwise regression model like we had for the time of week and temperature, or whether we actually have a different configuration of coefficients that allow us to map temperatures, time of week, and GHI to energy.
Mm-hmm. So it's different. Let me stop sharing this. I think we have this in the appendix. I don't know. I'm trying to find if we
I'm
have.
sure you guys showed it
here
at some point, and I just
yeah.
I don't remember now.
I mean, I just go ahead and explain it. So basically, we have two main segments. One, for the input, we have time series features. It has to be temperature involved. That's for sure. We're forced to have it. And we can have GHI, or global horizontal irradiance. So these are the time series features, and we get it as a matrix of, let's say, we can have different lags defined, but as of now, let's say we want to predict 1 day or train 1 day. So we have 24 hours of temperature and 24 hours of GHI. And this is a matrix of 2 by 24. And this is going to be our input features time series. And then we have a categorical variables. Categorical variables in this case, because we are using that time series. Right now, we don't need the time of the day anymore because it's already in it. We can see that as a time series. And in the categorical variable, we have day of the week, which is 1 to 7 or 0 to 6, if you want to index it. And we have month of the year, 1 to 12 or 0 to 11 again. So these are one hot vector for the categorical variable. And the matrix that we had is actually will become a vector, and all of those things would be a huge vector as an input to our linear regression or elastic net. And the way we model it, we get all of that and map it to the 24 hours data. So we get 24 hours of input. We are mapping to the 24 hours. So basically, the weights that we have is actually a matrix. It's not a vector anymore. It's how many input we have. Let's say 69, which is 2 multiplied by 24 plus 7 plus 12. So, and then multiply by 24. This is a matrix of the weights that we have, and that is actually multiplied by the input. We will predict for the 24 hours. And what we do with those coefficients during this optimization and training with ElasticNet, we're trying to train it and restrict these weights in a way that we have the well-fit model. And how we do it based on that hyperparameter optimization for the whole population. And Travis.
So to come at that from a slightly higher level, not that anything that Armin said is just wrong. It's just very low level. No, we do not have any kind of switch to go from one linear regression to another. And if we think about this, like that's what Caltrack 2.0 was doing. And we've already shown that that overfits your model. So the only way that we can do something like that in the future is to have it so that something like that will also be pushed. The coefficient for that will be pushed towards 0 so that that doesn't occur, which is a difficult problem in itself. But as it stands, we've already shown that basically having a very complex model where you have all sorts of breaks and you allow for all of these different changes, that is worse than just having a penalized linear model.
So, and again, like I wasn't trying to argue for going back to the other model. I just want to understand like what the constraints are in this model so we understand which things it might do badly for. You know, one example of this is like sometimes I've had people come to me and want to talk about using sub-meter data, and then should we use EEmeter for it? And sometimes that's fine. If you've got an HVAC system and you want to use sub-meter data on it, like no reason why it shouldn't work about the same way as building data. It might be even better. And there's other things where you're like, no, that's not a good fit. And we could get into the supplemental data conversation. But I'm still not sure if I am fully, I mean, like I'm getting a picture of a matrix of weights. It's a fairly large matrix. If you serialize the model, and this is maybe you're going to hear me sort of making a not so quiet plea for interpretability of the coefficients and try to understand, if you were to serialize the model, would we be able to identify a heating or cooling slope or anything like that? I mean, I hear that there's an hour of week and a month of year and a day of week, like that those all have weights in the model. But it sounds like we haven't gone to a balance point and degree day model, but temperature obviously has a relationship. Yeah. Does temperature have a different linear relationship essentially for each hour of the year effectively, or?
It depends on the meter itself. We will basically, it's purely data driven, and we let it the model and the training or the optimization decide what's the relationship for each meter. So we're not bounding it by the balancing point. We don't even have that in our definition at all. So if pretty much you can plot, which I did, just to have an idea of what's going on in that matrix. You can plot the heat map, and you can see actually, oh, there are some portions of the data that has more importance for the prediction. For example, for the GHI, you can see it's more brighter for the solar customers in the middle of the day rather than for the non-solar customer in the middle of the day. But you can just have a glance, but there's nothing that you can interpret, in my opinion, with just simply look at the coefficients.
So then let me play devil's advocate and turn it around backwards. Yeah. Going back to the sort of overfit linearized model that is high on interpretability and has other problems, where I said, oh, well, the solution to saturated HVAC and saturated inverters is add more model coefficients to allow values that exceed a certain point to exert that kind of negative feedback and flatten it out. Obviously, we don't have anything that is specifically one way or the other, but from what you're saying, I don't see any reason why we wouldn't expect that an HVAC system that's saturated or an inverter that's saturated that has a very consistent response to temperature or GHI that's above a certain point. You haven't described anything to me that says that this model wouldn't find that signal if it was strong enough. Obviously, if there's only like 1 hour of the year that's saturated, well, though we don't expect that finding a day that's 10 degrees hotter than that suddenly does something clever. But if we had a system that's saturated 10% of the time in the summertime, why wouldn't the model actually predict? We could look at this, right? Like we could look at a saturated PV system and do model versus actual and see a dumb model will make a nice sine wave in the middle of the day. And maybe this model will actually show a roof, a ceiling, and cap it off.
That's actually
Is that a reasonable assumption?
Yes, 100%. That's exactly why we don't define extra restriction for the model and let the meter data itself decide what is the model coefficient should be. If we consistently have a cutoff in the middle of the day, then the model should learn that pattern from the training set, and hopefully we have the same pattern inside of the test set, because we're just looking at the covariates, which is temperature and GHI. So if that's the case in training set, and we train the model to learn that, we should be able to see that on the other side, which is the test set or reporting year.
Okay.
And one more thing, just like a quick hack. Sorry, Trav. If we are 100% sure that there is a cutoff for the inverter or something, we know that it has a relationship to the GHI. As a test for R&D, I don't suggest it for the whole thing. Why not changing the input of the GHI that you have as an input to be saturated, and then pass it to the model? But that's just basically me thinking in the research base. Travis,
well, the way to fake out the data is less about showing GHI pegging at 1,000 watts per meter squared arbitrarily, and more to just put a cap and set your solar. If you had just solar data that you were putting on there, just set that to a min of, take a 6 kW solar data set and say it's a min of 4 kW or the actual, and then you'd get a cosine with a ceiling on it, and that's what it would look like if you had an undersized inverter. So but I mean, generally, yeah, we could make a fake data set. We could test this out. 100% agree.
Yeah.
I would just push back a little bit on the idea that Caltrack 2.0's hourly model was in any way interpretable. Like, does anybody actually look into those coefficients? Because it's probably a matrix as large as what we currently have.
That's totally fair.
Exactly. You can have a heat map for that. This is more meaningful than the other one, actually.
Yeah, no, I'm not going to defend Caltrack 2.0, but the coefficients all had units. So we had the hope
No.
someday.
So it wasn't interpretable. There was just a hope that one day someone might do enough work that it was.
Well, I think, it's worth remembering CalTrack 2.0 had its roots in the LBNL time of week and temperature model for demand response, and then was that was the starting point, right? So
Yeah.
a lot of that kind of structure of the model had been previously established, and I think it comes back to this question of, what do you want to prioritize? Do you want your model to disaggregate heating and cooling loads and other types of loads? Do you want your model to produce an accurate counterfactual? And we've always approached this working group, with a fresh set of eyes on that question. And I think we've made, by and large, the right decisions. The daily model has typically been, the disaggregation of load has been a really important feature of the daily model. So we started with that as something that we wanted to retain, and we did. But the hourly model really hasn't been used for that purpose. And I think with AMI data and all the use cases around EV charging and solar PV and demand response, and like the real need to develop accurate counterfactuals on an hourly basis, then we don't want to try to split our allegiances here. And we want to have a model that first and foremost develops accurate hourly counterfactuals, and can work at scale, because as we've talked about many times, we need to apply this model across many thousands of meters, or even more at times.
Yeah, I mean, I'll tell you the thing that I'm really hoping that this version of hourly does better than the old 2.0 version of hourly is the model fit really well, except on the highest peak days. And so I'm working on grid capacity planning projects now. So it's really embarrassing to say, like, oh, our model's got a great CVR-MSE. Here's your peak day. Yeah, we're off by like 10% on your peak day, but all the other days fit great. So I'm really curious to see whether this model does better, or whether it's still a thermal lag issue, and that's a next step.
Going back a little bit to the question of, this is both daily model as well as hourly model potential future, as far as having this cutoff point, is that one thing that is really, really important to remember is just how noisy this data is. We can say from an engineering perspective, yes, something is supposed to have a cutoff at approximately this value, or at least it'll be tailing off AC, solar inverter, whatever. There is still going to be a significant amount of noise in your data. And so you have to basically fit a model that you're only going to get a break there if the signal is greater than the noise. And in a lot of cases, the answer to that is no, even if as an engineer, you might say the cutoff and the break point is here. And if we're talking about full-on automation, like, we have to go with a plan that is not human intervention.
Yeah, no, I 100% with you, Travis. The interesting use case that I might have coming up, that I'll let you know if I get to test it on hourly data, if everything works out this way. Hybrid heat pump systems where they fall back to fossil fuel at a low temperature. So we're going to have a strong temperature response on the electric side between, say, 50F and 20F, and then below 20F, we're going to literally have a thermometer outside that trips over and goes back to gas heat at that level. And so all the electric heat is going to disappear based on outside temperature below 20F. And, traditional daily model, had no hope of doing anything useful with that. Be very interested to see where some of the new ones are able to make of that. So generally speaking, I hear what you're saying. A lot of these cases, when we see saturation, it's a little bit of like fuzzy noise at the tail of one of the temperature extremes, and it's hard to actually have a like physically meaningful response to that. And I totally agree. Occasionally there's more interesting cases, but it's just rare that like we have an interesting case, we know what the answer is, we can test the model against it, and then like look at the model results and say, oh, can we see evidence that the model is like being misled to use an anthropomorphizing term, like is it being misled by this particular temperature response characteristic in the physical system, or was it able to accommodate that within the model somehow? For the most part, like we have no idea, right? There's like a table of error and savings, and there's hundreds of projects, and we just move on.
Yeah, as far as daily goes, I think that this is something that we can definitely improve upon because, Armin, can I share my screen real fast?
Yeah, I'm not necessarily expecting the daily to be able to roll with this yet, right?
No, it can't. This was one idea. Oh, wait for it. This is one idea that I had on how to be able to do this within the daily model. And that is, this was actually a case that I was showing semi-frequently whenever we were working on the daily model. And so you can see like even the current daily model, it splits on summer. So you get this model up here, but then you get a separate model for winter and shoulder. Whereas if we were to just draw a line, we would draw something more similar to this red curve. And my idea on how to make it so that the model could do this is to actually make it so that the heating could have its own breakpoint where it could change slope, and the cooling could have its own curve where it would change slope, and the smoothing here would introduce the rest of that. But basically, that would mean that you could have a flat line that would depict this, another line that would depict this part right here, and then a smoothing part in between. This is definitely possible within the current daily model. It's just that we had to reach an end somewhere, and it was before this. So this is
Well,
kind
and
of like the next step that I think would be an improvement.
yeah, I mean, unfortunately, the scenario that I'm looking at of the hybrid heat pump systems is even worse than most of the ones that we've talked about so far, which is that it's not just a break in slope, it's an actual discontinuity. So you're going to go from, you're going to see the electric demand per day rise as the temperature drops, and then you're going to hit a temperature, and then the expectation is that below that temperature, you're actually going to flatline. You're going to go back to just base load because the heating load is going to entirely switch to a secondary system that's fossil fuel, and so you'll have just a straight up discontinuity in the linear regression, and so only something that's doing more like a bin analysis and isn't assuming that there's a contiguous line like all of our models have always assumed, is going to be able to follow that with any satisfaction.
I think a use case like that would really bring up the question on, is that something that we really want to model with a regular model? Because to do that would require that we have some sort of a step change function. And then you can't just say, oh, we're going to allow a step change function on this meter, but no other meter. So then we would be allowing step changes for every meter, which means that we would never have, in practical cases, we would never have continuous models anymore.
I mean, this is such a good,
Yeah.
we don't talk about this much in this working group, but maybe we will in the upcoming months, but we don't talk much about comparison groups. And, you know, outside of this working group, we've also done a bunch of work led by Travis on comparison group selection. And in fact, we should talk about this a little bit. Maybe next time we can more formally just take 10 minutes and talk about this. But we just released a new version of the open source GridMeter code base, and we released a new version of the GridMeter report And in both of those places, we have incorporated a methodology called clustering, and it's exactly what it sounds like. You use clustering algorithms, scikit-learn, and a bunch of like principal component analysis and stuff like this. But the upshot is that in this method, we are selecting comparison groups and we're forming those clusters based on model error profile. So, potentially if you have a system like you're talking about, Ethan, where you literally have like a step change, and there are enough other buildings in the population that show similar behavior, you're going to select them into the comparison group. And that's ultimately a way that you can account for that. I think like there's always a big gray area between what do you want the baseline model to do versus what do you need the comparison group to do. And I think that, in the daily model, it used to be that we were relying on the comparison group to take care of things like seasonal bias. And it was pretty obvious that like seasonal bias was a problem that was coming from the baseline model. And it was absolutely addressable. So we did that, we've seen comparison groups like really struggle with solar PV customers. You don't really get the correction you need out of the comparison group when you have the issues that Caltrack 2.0 hourly has with solar PV customers. So we really need to like bring that into the model proper. But some of those kinds of things, it's I don't necessarily have a strong opinion one way or another, like on whether the exact use case you're talking about should be something that needs to be considered by the baseline model, or if it could be well handled by a comparison group. All I'm really saying is that when we make measurements, we almost always have a comparison group at this point. And that comparison group, is around for these kinds of things.
Yeah, I mean, this use case is, I mean, one, it's probably an outlier in terms of what this working group tackles. In this case, these heating systems function in the performance period, not in the baseline period. So the good news on the one hand is you can make a nice clean linear model from the baseline period, and your actuals are easy because as weird as the model gets in the performance period, your counterfactual is fine. But if you want to do any kind of diagnostics, or if you want to do weather normalized forecast of lifetime savings, that's when life gets tricky again. And I don't think the comparison group 100% gets you out of that. But I'm not bringing it up to look for a solution or to cast any aspersions on the quality of what we have here for 99% of the use cases that are out there. Just to share some of the more interesting cases that we're getting into as like heating systems are getting more and more complicated as we move into this like electrification transition phase. Just so we have some mental models in place sometimes as we're thinking about like, all right, what are the trade-offs with our model specification, and how do we like just express, particularly I think as like the folks in this group have like gone down the rabbit hole on the hyperparameter fitting and like stuck it out this long. We are the ones who need to talk to like the much larger group of program managers and even some of the larger like evaluation community who are trying to figure out where does the e-meter fit in the rest of the space of other solutions that are out there, and what are the appropriate applications, and how should we interpret some of the results from it. And so that's just why I bring up some of these thought experiments of like, okay, how do we sort of translate this back and forth. But I just want to be clear, like by and large this all looks like a huge step forward, and I'm super excited. I'm gonna take one more minute just to put a yes vote on your last bullet, Armin, about the like, should we keep the supplemental data exposed? And I would just point to the philosophy that we've had for a long time in the API, which is a lot of the things that are like the Caltrack savings method, which is how much bad data do you allow what are the model quality coefficients that are thresholds for disqualifying a site, things like that. Like those are defaults, but you could override those in the API, right? If you want to use the model for some kind of R&D thing on the side that's not like a Caltrack NMEC savings project, so that a large group of people could still take advantage of the code, but it's still easy to get consistent answers. And I would argue for that same philosophy. Like don't make those of us who want to tinker have to do weird things like, oh, global horizontal irradiance, of course it is. This isn't pressure from an industrial process. No, it's GHI. Just model it. Like it'd be much cleaner to allow other stuff to come in if we want to see how the model does with that. I think we'll learn more from the community that way.
Yeah.
It's a separate question if there's like a standard reporting file that comes out of a Caltrack run that you should show to say like, hey, this is the set of inputs I used, so no one has any misunderstandings about what the assumptions were.
To clarify, we definitely don't want to hide this functionality where it's going to be available. It's more of a question of like with the data class in the default settings, we're basically saying this is OpenEEmeter replacing Caltrack. You need to use it this way in order to use it for your savings measurements for various programs. Now, can you use something other than those defaults? Of course you can, but that's not going to be. We're not going to say that is like the calibrated measurements that you should be making. You can still do whatever you want. And so the question as far as supplemental information is what do we restrict? Do we say like what kind of supplemental data can be put in? And so we're kind of wanting to open up that debate of like what is going to be something that we are basically willing to put the OpenEEmeter seal of approval on.
Gotcha.
Two things real quick. One thing about the GHI and any external supplemental data, at least for the GHI, for many locations and many recent years, we need to pay for it. We need to subscribe for within some companies like Soulcast or other companies that are providing data. But till end of 2021, we can use the NREL dataset. That's one thing that actually can restrict many people to use the GHI because we need to pay for it. And that's one thing that we need to consider and we need to talk about it. And because right now the model is almost finalizing by itself. And we need to have that conversation of how we want to approach that. And another thing I wanted to mention about the Matt question. So basically, there's a mixture of meters. Some of them are exporting more because we're in California. Solar is a lot, and then net most of the year is negative, specifically in summer. And for some of them, with the bigger load consumption and smaller solar PV systems, that can sometimes touch the negative, but sometimes and most of the time it's positive. I don't know if I understand the question right though. Okay. But probably when we go to the commercials, we're gonna see more of those that the net is positive, but we still should be able to see some sort of pattern of solar inside of data. I haven't worked with the commercial data a lot. I'm looking forward to it, to actually dig into it and see if the new model is working. How does the load shapes look like in the commercial data and so on.
Can I actually drill in one more step to that? Because some of the data that I've seen for modern interval meters has actually separate registers for each direction. So within a given interval, you can see both import and export, because it's of course measuring at single second or sub-second rates, right? It's got to be doing a full, 60 hertz, better than 60 hertz. So it'll have a 15-minute measurement that says, well, we got, a little bit in, but then mostly we pushed out, or vice versa. I assume, well, actually, I'm not going to assume, is the best practice to sum up those registers and create a true net register. So even if you know that there was some in and some out in a 15-minute or an hourly period, you just go ahead and, add them together, fix your signs as needed, and get the positive or negative net for each interval? Or is EEmeter expecting 2 data streams, one for import, one for export, and they don't have to, they could both be non-null in one interval?
Right now, it's just give me the AMI data, which is the summation of all of that. But that's something actually we can think about it, because I saw in a couple of the data sets that we have 2 columns. One of this import and the other one is export. I haven't thought about it in terms of this setup right now, but this one right now, we just get one column as output. Yeah.
But I would be clear in the documentation about that, because give me the AMI data. What I'm describing is AMI data.
Yeah.
It's it's potentially
stream,
a little more raw, right? Like the AMI data that I usually see is like there's import, export, and then there's a computed net that may or may not be, computed at the meter. It might be computed further along in the MDMS or the CIS or something later on.
Yeah.
And so depending on who you're getting the data from, you might have to compute the net.
So we usually go with net, and I have put some thought into this, and that is because of the interval at which we receive the data. And things get really messy really fast whenever you're having like 15-minute, 30-minute increments where one's negative, one's positive, but it's so distant in time that it's better just to net those out. Whereas if you were to be able to get something at a smaller time increment, maybe something like a minute or less, then I could see their value in having 2 different streams, because then that would be much closer to what's truly happening. Now, best of course would be if you could have true net and X, or not, because they're netting it at the AMI device per that increment.
Yeah.
But if we could get 2 different streams of here is export and here is import for the same exact time periods, that would be, if that were the case, then I would say to always use them separate.
And that would be sub-meter data, and we don't even need, we just subtract, then use the export data to model.
Yes. Yeah, you would basically have the sub-meter solar data at that point.
Right. So most customers in Vermont have that set up. I think there's only maybe one other state, I keep forgetting which one it is, that did that. Basically, the tariffs in Vermont allowed you to get paid more for generating solar, even if you didn't export it. You got an extra 4 cents a kilowatt hour or something, even if you self-consume. So the way to take advantage of that tariff was to install a second meter at the generation point. So there's like 4 registers, because you also see it consume a little bit for the inverter during some periods when it's not producing and stuff like that. So the Vermont utilities have all that data, but like no one else does. So no one ever builds software for for the kind of data that we have here. So I wouldn't worry about that edge case, but I hear you. So I think that's a totally reasonable answer, and I would just recommend make it clear in the documentation that people should just be careful and make sure that they check what they're getting, because it's not always obvious. Like a lot of times the AMI data, it doesn't come in like columnar. You're getting reads, and each read has a timestamp and has a register type, and it has a value. And so you might look at a few rows and be like, oh, there's a timestamp. This is a consumption read, and there's the value.
I hate to interrupt.
Yeah, I know we're over time. I'm sorry.
Can you wrap this in like 15 seconds?
Yep. Just check for non-duplicate timestamps and make sure they're net. That's all.
Absolutely. All right.
Sorry about that.
Well, No, it's okay. We've already gone over. I just figured that I should hammer down now.
No, I
All right.
appreciate that.
Thank you everybody for coming, and we look forward to the next meeting. As always, if there's anything that you would like to present yourselves, you're doing your own research, we are happy to include that. So just message me, Adam, or Armin, email, whatever. And hope you have a great time in the interim.
Great, thank you guys. Appreciate it.
Thanks, everybody.
Good work.